Okay, so so let's keep identifying these different parts of the periodic table. We looked at the alkaline metals, the very first column. The second column would be the alkaline earth metals. Transition metals would be in here, these ones, okay, that block. The inner transition metals would be down here, all right? And the metalloids are these ones right in here. We identified those. They're kind of pink. And now we're at the nonmetals. So nonmetals would be found right after the metalloids, just right in here. Okay? These would be the nonmetals. Everything else is, besides those few metalloids, everything else is a metal on the periodic table. Okay? So those are the nonmetals over in here. Halogens. Halogens is a special group on the nonmetals, found right here, group 7A or 17 in this periodic table. Fluorine, chlorine, bromine, iodine, those are halogens. That's a special family. Okay, they all have very similar reactivities. Noble gases, that would be the very last column of the periodic table. Right there. And those guys are the noble gases because they are inert. They don't react with stuff. And there's a reason for that. The reason for that is because they have a full valence shell. And we're going to talk about what that means. But these guys, they like being the way they are. And all these other elements, they have these tendencies to either lose electrons or gain electrons, and that tendency causes them to become reactive. Whereas those guys, helium, neon, argon, krypton, those noble gases, they are non-reactive because they don't have that tendency. They enjoy being the way they are. And we'll talk about that, what that means. Okay, so here we can see some of those groups found on the periodic table, kind of without all the elements. The noble gases, the halogens, alkaline metals, alkaline earth metals, transition metals here. Okay, so those are some of the groups there. All right. Okay, so let's talk about compounds then. So there's different types of compounds. We have ionic compounds. There's two types. We have ionic compounds, and we have covalent compounds. Okay? So how do we define an ionic compound? An ionic compound is a compound that has elements which have become charged, meaning they have a positive or a negative charge. Okay? And those positive and negative charges allow them to come together and form a compound. Okay? They form ionic bonds. The attraction of the ionic bond is accomplished because of the opposite charge, but they have the same magnitude of charge. Meaning that one electron is just as strong as one proton, but just with an opposite charge, and so they attract with the same force. Okay, precisely with that same force. All right, so they have the exact same magnitude of charge, but just opposite. So you have a positively charged thing, you have negatively charged things. Okay, so metals, I'm going to add here, metals lose electrons. Nonmetals gain electrons. Those are their tendencies. If you are a metal, you will lose electrons and you will become a positively charged element. You'll become ionic. with a positive charge. So magnesium is a metal. It will lose electrons, and it will gain a positive charge. Because if I lose electrons, that means the number of protons I have is outnumbering the number of electrons that I have, and so therefore I am positively charged because I lose electrons. You cannot change the number of protons. Magnesium has exactly 12 protons. Its atomic number tells us that. Magnesium number 12 has 12 protons. That number will not change if it's still magnesium. If it changes, it will become sodium, or it will become aluminum. But as long as it has 12 protons, it is magnesium. The only thing it can do is lose or gain electrons. So if it loses electrons, it becomes positively charged. If it gains electrons, it will become negatively charged. So you kind of got to think about it backwards, right? Plus is minus, minus is plus. I lose electrons, I gain a positive charge. So the metals do that. That's what they do. They lose electrons. They become positively charged. Okay, even this guy over here, lead or tin, they lose electrons. But once I pass this barrier right here, okay, these are all metals. They lose electrons. I get into the nonmetals. The nonmetals do not want to lose electrons. They don't lose electrons. They gain electrons. So these guys are going to have what charges? Negative charges. They're going to have negative charges because they gain electrons. And by gaining electrons, plus is minus, I have a negative charge. Okay? I have a negative charge. Okay. So sodium has equal number of protons and electrons. Okay, a sodium cation has lost an electron. So it has one more proton. It has 11 protons, then 10 electrons. Now it has 10 because it lost one. That gives it a 1 positive charge. So it becomes Na plus. Okay? So that's how we would identify it, because it will lose an electron. That will change its charge. All right, so we're going to talk about a model of how we can look at these elements, okay? And the Purok table is going to help us understand this model. We call it the Bohr atom model, okay? And we're just going to start with a nucleus. And this is going to really help us visualize what's going on with these electrons. So Bohr was a scientist that wanted to understand the positions of electrons on the element. Okay? And he did that by spectroscopy. He would shoot energy at the electrons, excite them. They would move up in energy levels. And when they would relax, they could only relax by releasing energy. And the amount of energy that they released would tell Bohr the exact position of that electron within the element itself. Okay, so that's what he was determining. So here's a nucleus, and let's just start with hydrogen. Now, do you see the numbers on the side of the periodic table? 1, 2, 3, 4, 5, 6, 7. Those are energy levels. And this is going to become more important when we get into later chapters, when we start talking about electron configuration. But right now, to understand what's happening with these electrons, these 1, 2, 3, 4, 5, 6, 7 on the periodic table, those are energy levels. And an energy level on our atom model is going to be represented by a circle. Okay? This is the first energy level. That means the electrons in this first energy level, they don't go past this energy level. That's where they are. They're in that energy level. It's the closest energy level to the nucleus. Okay? So that's the first ring. We're starting with hydrogen. Okay? Hydrogen has 1 electron in the first energy level. Now, what I want you to notice about the periodic table back here, okay, is it is broken up into 4 groups. You see this group on the periodic table? It's the first 2 columns. It's pretty. You can identify it pretty easily, right? That's a group. You see this group on the periodic table? Boron, carbon, nitrogen, oxygen, fluorine, neon. Everything under those, that's the second group. Okay? And then you have your metals in the middle. Those transition metals right here, that is another group. And down here, this is your last group. These groups have names or letters, okay? I guess initials. S, P, D, and F. Okay? Electrons, they are in those principal energy levels, 1, 2, 3, 4, 5, 6, 7, like I just mentioned. But they are also broken into sub-energy levels within the principal energy level. Okay? So hydrogen is in the first principal energy level, and it is in the sub-energy level S. So its electron is an S electron in the first energy level. Helium, for purposes of what we're doing here, helium is not over here. Okay? Go away. It is right here. Helium is also an S electron. The only reason they put him over here is because he's a noble gas. He's inert, just like these guys. But he doesn't have the same characteristics as these. Okay, so he is actually an S electron over there. Okay, so for what we're talking about right here, the Bohr atom model, helium would be right here. Okay, so you have hydrogen and helium in the first principal energy level, sub-energy level S. Okay? And then, from there, we go to number 3. Where is number 3 located? Which principal energy level? No, not the third one. Lithium is in which?
Oh, second.
Second. It's in energy level 2. What sub-energy level is it in? S. Beryllium? Same. 2S, right? Now, we get to boron. Boron is in which principal energy level? The second. What is its sub-energy level? P. Good. Okay? So the periodic table is arranged for us to see the principal and sub-energy levels that the electrons fill when they are filling onto an atom. And this is what Bohr, this is what he discovered through spectroscopy. Okay? So let's continue on our model here. Okay, hydrogen, helium. They're both in the first principal energy level, and they pair because electrons pair, and they only pair in their groups. S electrons do not pair with P electrons. P electrons do not pair with D electrons. And D electrons do not pair with F electrons. Okay? So they all stay in their pairs. S, P, D, F. These guys pair. They're all pairs. You can see that. And then these guys, they fill 3 positions, and then they pair in those positions. So you'll have 3 pairs within the P's. You'll have 1 pair in the S. How many pairs are you going to have in the D? How many elements do I have across the D right here? From scandium number 21 to zinc number 30. 10. How many pairs will I have?
5.
I'll have 5 pairs. I'll have 14 electrons on the F. That'll give me 7 pairs. Okay? So that's how they pair. They pair within their energy, their sub-energy levels within a principal energy level. Okay? So hydrogen and helium, they are pairing right here. The first principal energy level is completely full. It's completely full now. The first principal energy level can only hold 2 electrons. That's it. Okay? And after I get past the first, I go to the second. Now I'm into the second energy level. Lithium and beryllium, they will pair in the S subenergy level. Okay? Then I move to boron. Boron is not an S, so it will not stay in the S subenergy level. It will go into the P subenergy level, and I'm going to make that red electrons that are representing P, and P for the principal or subenergy level P there. Okay, and you'll get boron, carbon, nitrogen. They all spread out individually, and then oxygen will come back and pair with boron, fluorine with carbon, and neon in the end. How many electrons are on this energy, the second energy level right now? 8. 2 S's and 6 P's. So I have 8 electrons on my valence shell, what's called the valence shell, the outermost shell. That is an important concept for what we're talking about with these ions. Why do the ions become what they become? Because they want 8 electrons on their outer shell. That's why they do what they do. They want these 8 electrons. If they don't, so let's go back to fluorine. Whoops. Okay, so for fluorine, okay, fluorine has 1 electron missing, right? From having 8. It doesn't like that. It's annoyed. It doesn't want that. So fluorine wants to fill that vacancy. So what does it do? It takes an electron, puts it there. What happens to its charge? What does it become?
More negative.
F minus. Because it fills that vacancy, right? It fills that vacancy, and now it has a negative charge because it has 9 protons, but now it has how many electrons? 10. So the number of electrons is outnumbering the number of protons, and so it becomes negatively charged. Okay? All right, let's go to the next one. Let's go to the next energy level. Sodium. Magnesium. Okay? I'm in the third energy level, right? Sodium and magnesium. How many valence electrons does magnesium have? What's that? 2. It has 2, right? How many valence electrons did sodium have before I added magnesium? 1. It had 1 electron. Magnesium has 2. Okay? These are the valence electrons. Magnesium is a metal. What is it? What is the tendency of a metal? To lose electrons. Because guess what? It has 2 choices. It could either gain, magnesium could gain 6 electrons to get to here, or it could lose 2 electrons and get where? Right back here. So if magnesium loses 2 electrons, it has 12. It will then have 10 electrons. So if this is magnesium and it loses both of its electrons, look where it is. What is its charge? Not negative. positive. It lost electrons, which means it's positively charged. That's confusing sometimes. It's kind of backwards, right? So if you're dyslexic, you're doing great. Okay? So magnesium has what charge? Positive how many? 2 positive.
So what's the energy? It's like, I remember it's like 2, is it 2, 4, 8? The valence shells or whatever? Or is it just 2? Like for the 2 electrons, for it to be stable, right? Because it wants 8.
2 is stable if it's the first energy level, but after that it's 8.
It's
the
8
whole
all
time.
day?
Yeah. To become stable. Yeah. Okay? So that's why helium's right here, because it's stable with 2. But after that, these guys will all have 8 electrons. 8, 8, 8, 8 on their outermost shell. Okay? Their valence shell. Because that signifies stability. Okay? So, all right, let's add those back. So we have those there. And then we put in our p electrons. So we're going to jump over to Al, 1, Si, P. They spread out, and then they come back, and they pair. Sulfur, chlorine. Actually, let's go back to sulfur. Okay? Sulfur has how many valence electrons? 6. Do you see how it has 2 electrons that are unpaired? Doesn't like that. So what is it going to do? It's going to gain 2 electrons. And now it will become what? Sulfur. What's the ion of sulfur? Yes. It's going to have a -2 charge on it. It's going to gain 2 electrons, 2 minus. Okay? So it becomes S2 minus. This is sulfur. This is how I know what type of ion I become from the periodic table. This is how I predict ions. What type of ion will everybody in the first column of the periodic table become? What will be the charge of all of those metals in the first column when they lose an electron? +1. How about everybody in the second column? +2. Okay? So you see how the periodic table is your friend? It tells you what type of ion they will become. Okay? What type of ion is nitrogen going to become? It is minus, but not 5. It has 7 electrons. It wants how many? -3. Excuse me. 1, 2, 3. It's going to gain 3 electrons. Okay, do you see its position, how it does that? 1, 2, 3. It wants to get here. What about phosphorus? Is it any different than nitrogen? No. It's exactly the same. How many valence electrons does phosphorus have? 5. Nitrogen? 5. Arsenic? 5. They all have 5. How many do they want? 8. So what type of ion are they going to become? -3. How about these guys? -2. How about these guys? -1. That's what it's about. That's how I can predict what type of ion I am going to become using my periodic table. If I understand what's going on here, it's all set up right there on the periodic table. Okay? Now, there's a little bit of a trickiness once we get into the 4th energy level. Do you see what it is? You hit the D's, right? The D's are a little bit out of order. So, let's go ahead and add a D. The 4th energy level. Here's the 4th energy level. Okay? I'm going to add my S electrons, potassium, calcium. But now, where am I? Scandium. Scandium is not an electron that goes on the outside. Because if I get here, remember we said once we get to krypton, how many valence electrons will I have? 8. How is that possible if these guys go on the outside? It's not. They don't go on the outside. These are not outside valence electrons. D electrons are never on the outside. Only S and P. The D electrons actually fill inside to the sub-energy level right below the outside energy level. Okay? So, let me kind of reiterate it this way. The first energy level has one sub-energy level in S. The second energy level has two, S and P. The third energy level is even bigger, and it has an SPD. The fourth energy level, SPDF. First has one, second has two, third has three, fourth has four. How many energy levels do you think the fifth principal energy level has? 5. S, P, D, F, and G. There is no G on the periodic table. You would never get there. Okay? We would never fill a G ever. Okay? So the fifth energy level and beyond will never be full. Only the fourth will ever be full. Okay? So these are the sub-energy levels of the principal energy levels, and so forth. All right? So looking back here, the third energy level has a what? A D. This is the first D. That means it must pertain to the third energy level. Okay? So I have my fourth energy level here. And now I want to fill the D electrons. They don't go on the outside. They go on the inside. Whoops. That's not what I want. One, two, three, 4, 5, 6, 7, 8, 9, 10. Okay? So it fills with those 10 electrons on the third energy level, not on the outside. Once I get to zinc, now I'm here. Where does this guy go? Does it go on the third or the fourth energy level? On the fourth. Okay? So now I'm going to add my 4 P's. 1, 2, 3, 4, 5, 6. Here I am. How many valence electrons do I have? 8. Okay? That's how come every time I get to the end there, I only have 8 valence electrons. Okay? Because D and F are not outside electrons. They are inside electrons. So when I predict the charge of an element, I cannot do it for these guys. I can't do it because they do all kinds of weird stuff with their electrons. What are the valence electrons of these? How many valence electrons do these guys have? Iron? How many valence electrons would it have? Where are the valence electrons before you hit iron? Has 2. You have 2 valence electrons. Okay? So iron could lose both of those, or it could even lose 3 electrons because one of its electrons out in here might come out to the valence shell and get lost. Okay, it can do all kinds of stuff. Or it could only lose 1. You have iron plus 1, iron plus 2, iron plus 3. You have all of those. So I cannot predict from the periodic table which iron I have. I cannot do it for any of these D elements except, there's 3 exceptions. You got to write these down. Zinc, Zinc has a 2 positive charge, always. Cadmium, 2 positive charge, always. Silver, +1 charge, always.
Which one was this?
Silver, Ag. This is zinc, cadmium are both 2+, and then silver is +1. Okay, those are their charges always. So if you ever have a compound with cadmium, you know the charge of it. It's 2+. If it's zinc, you know the charge of it. It's 2+. If it's silver, you know it's +1. Now, Al. Al is a metal. How many valence electrons does it have? 3. We can predict the charge of this metal. What do you think it's going to be?
-5.
No, not minus. So if you were going this way, but we're not going to. This is a metal. Remember, what do metals do? They lose. 3+. It will become Al 3+. It is the only metal in the P block that we can predict. Because look at all these other metals. See all these other ones? What do they have to go through? They have to go through the Ds. We cannot predict the charges of these guys. Of lead or tin, I can't predict it. It could be lead 4 or lead 2+. I cannot predict it. So when we are identifying the charges of metals, we have to do it within the compound itself. Okay? Because the nonmetals will tell us the charge of the metal in the compound. And we'll look at how that works. Okay? Okay. So here's, you can see all of these are +1. All of these are +2. Let's see. Let's blow that up a little. Okay? +1, +2. You can see chromium here, +3 or +6. Okay? So it's kind of unpredictable. Manganese, 2+. There could be others. You can have 4+ on there too. Okay? Iron, 2+, 3+. You could have +1. They're not showing all of them. They're just giving you kind of this idea of what's going on here. Zinc, cadmium, and silver. Those are always the same. 2+, 2+, 1+. Al is always 3+. You see, we can't predict these ones. Okay? -3, the nonmetals. -2, -1. They're neutral. They don't lose or gain. They're the noble gases. Okay? So that's kind of what we're looking at. That is going to be very important to you when we start naming compounds, because we are going to have to identify their charges to name them. Okay. All right. Now, there are ions that incorporate more than just one element. Okay? So if something has more than one element, but it is charged with an actual negative or a positive charge, we call it a polyatomic ion. Okay? So something like this, CO3, 2-. This is CO3, 2-. That's an ion. It has carbon and oxygen in it, but it is ionic because it has a charge. So if you saw something like this, CO2, you might think, oh, carbon dioxide. But if I charge it with a 2-, now it's not carbon dioxide, it's an ion. It's a polyatomic ion. It's called carbonite. Okay? So we are going to learn how from our periodic table we can identify the different polyatomic ions. Okay? So we'll start here with carbon. And what you will do is you will start in the ATE section right here, 8. Carbonate has 3 oxygens. So you have a CO3, and its charge is 2 minus. Okay, so starting there, that's carbonate. Then I move over to nitrogen. Carbon to nitrogen. This is called nitrate. It's the ATE ending. Nitrate. It also has NO3, but instead of having a 2 negative charge, it has a -1 charge. Skip oxygen and fluorine. They're not going to form 8 polyatomic ions because you're just adding oxygen to these polyatomic ions. So, you know, there's no oxygen plus 3 oxygens. That'd be 4 oxygens. We don't have that. Fluorate is a theoretical kind of compound, but it doesn't really form. Fluorine's too electronegative for that to really take place. So we kind of skip oxygen and fluorine. And let's go to chlorine. So we're kind of going on the border here. Okay? When you're going on the border here, the number of oxygens is always 3. 3, CO3, NO3, ClO3. Okay? BrO3. IO3. Okay? Chlorate, bromate, iodate. Those borders right here, they all have a -1 charge. -1, -1, -1. So -1, -1, -1, -1, -2. Okay, for carbonate. So that's the only one in the border that kind of doesn't have a -1. So you can kind of think of it as -1 here. You start over at oxygen, -1, -2 as you go in. Okay? So you could imagine that borate would have a -3. -1, -2, -3. Okay, we're not going to learn that one. You don't need to. It's not a very common one. We're just learning more the really common ones. Okay? All right, sulfur. When I move from this border to the inside where sulfur and phosphorus are, I gain 1 more oxygen. So instead of having 3 oxygens, sulfate would have SO4 oxygens, as well as phosphate, PO4. Okay, so sulfate, as we go in, the charge increases. -1, -2, -3. -2, -3. Okay? So, carbonate, nitrate, chlorate, bromate, iodate, sulfate, phosphate. These are the polyatomic ions. I want you to learn how to do this. Okay? This is your starting point for these others. Because once you have the starting point, the rest of it is pretty simple. Okay? When I go from a 8 to a per 8, so if I go backwards this way, I simply have to add an oxygen. Okay? CO4, the charge stays the same. NO4 minus ClO4, whoops, minus BrO4 minus IO4 minus SO5, 2 minus PO5, 3 minus. Okay? These ones will be theoretical. They don't actually exist. But the idea is this. If you add an oxygen to your ATE8 ion, it becomes a per 8. What's the name of this one? This is carbonate. This would be percarbonate. What's the name of this one? Pernitrate. Perchlorate. this is the actually one that really actually exists, the perchlorate, okay? Perchlorate, perbromate, periodate, persulfate, perphosphate, okay? That's how you get the perate. You just add an oxygen to the ATE8 ion, okay? Going this way to the ite, I lose an oxygen. So it would be CO2, 2 minus. Oh gosh. NO2 minus. ClO2 minus. Do you see how the charge stays the same? You don't ever change the charge, you only change the number of oxygens. BrO2 minus, IO2 minus, SO3 2 minus, PO3 2 minus. Okay? These ones are very common. Okay, what's the name of this one right here? Instead of 8, instead of sulfate, it's sulfite. This one, instead of phosphate, it's phosphite. It's phosphite. Sulfite, iodite, bromite, chlorite, nitrite, carbonite. Okay? So you just simply lose an oxygen. You change the ending from 8 to ite. You lose one more oxygen. Now you've hyper-ited it. Okay? So CO 2 minus, NO minus, whoops, that should be N minus, ClO minus, BrO minus, IO minus, SO2 2 minus, PO3 2 minus. Carbonate, carbonite, hypocarbonite. Perchlorate, chlorate, chlorite, hypochlorite.
Phosphorus, is it supposed to be PO2 minus?
Oh, sorry, this should be 3. Thank you. That's a 3. That should be 3 minus. I should have kept the charge across there. I was getting too excited about -2s. Okay. Perphosphate, phosphate, phosphite, hypophosphite. Okay? So you got to keep your charge. You just reduce the number of oxygens. This is your starting point. Yes? Oh, excuse me. Thank you.
So is this only just for oxygens or like?
This is for oxy polyatomic ions. There are other polyatomic ions, okay, like cyanide, Cn minus, such that I'll probably have you learn. But these are the ones you can recognize from the periodic table. These are some of the most common polyatomic ions, and I would expect that you would be able to identify them in this fashion. Okay?
Okay.
All right. Now, the reason we need to know these is because we form compounds from these. And when we form compounds from these, we have to be able to name those compounds. Okay? So you'll be required to name some compounds based on that. Okay? So let's consider how we would put together some of these elements. Magnesium. If it is going to become an ion, what is its charge? Oxygen. That's right. 2 minus. How many oxygens and how many magnesiums do I have so that they balance each other to 0? This is an easy one. It's not a trick question. Yeah. How many of each do I need?
Just one of each. One of each.
That's the formula. That's what's going to form if I react oxygen with magnesium. Okay? How about between lithium and nitrogen? What's the charge of Li? +1. And nitrogen? 3 minus. Okay? Does everybody see that? We have 7 electrons, or it's 5 valence. We want 8, or we want to get here to 10, so I need 3 electrons. I need 3 more electrons. What is the combination here? How many lithiums do I need to balance the 3 negative charge on the nitrogen? Li3. N is the compound formula. Calcium. What's the charge? +2. Phosphate. Who remembers what it is? What is it? Okay, it's PO4 3 minus. That's phosphate. Okay? What is the combination? How many phosphates and how many, this one's trickier, guys. How many calciums and how many phosphates do I need? Okay, good. Well, you're kind of on the right track.
Yeah,
but okay, so the easiest way to do this is look at the charges. And if I have a 3 negative charge on the phosphate, that means I need 3 calciums. If I have a 2 positive charge on the calcium, that means I need 2 phosphates. 3 times 2 is what? 2 times 3 is, they balance, right? So you just simply switch those. So that means I need Ca3. Now look how I write the phosphate, because the phosphate is an entire one entity. Okay? So I use parentheses, PO4, 2 of them. I have 2 PO4s surrounding the 3 calciums. Or surrounding the 2 phosphates, I have 3 calciums. However you want to think about it. Okay? That's how I'd write the formula for calcium and phosphate coming together. Potassium and chlorine. K is what? What's the charge? +1. Chlorine? -1. So what's the formula? KCl, potassium chloride. Okay, it just comes together real easy. Okay, Al. That's right. It's the only one in that P block that we can actually predict. Oxygen, 2 minus. Exactly. What's the combination? Think about back here, kind of a similar situation as this one. How many ALs do I need? 2. How many O's? 3. They balance to 6, right? So Al2O3 is my formula. I call it the switchy thingy. It's a technical term. Okay? So switchy thingy always works. All right? Just switch this down, and it will tell you how many you need of each. Okay? What's the combination here? That's a 4, by the way. 4 plus.
Is that manganese? Is that in there?
It's manganese. Okay? This is not the final answer, though. Because what can I do to that formula? I can reduce it. This is my answer. Okay? Whenever I'm combining ions, ionic compounds, making ionic compounds, it always has to be in its lowest ratio empirical, it's called empirical formula. It has to be in its empirical formula, its lowest ratio formula. That is different than covalent compounds. Ionic compounds need to be in this state, the empirical formula. Covalent compounds are not. Okay? So that is a difference between ionic compounds and covalent compounds. Ionic compounds are always written in their empirical formulas. Why? Because they form crystals. They form salts, like sodium chloride. That's a salt you guys know about, right? It's in your cupboard. You eat it all the time. It gives you high blood pressure. So sodium chloride is in crystalline form, right? Well, I don't say how many sodiums and how many chlorines there are in the entire crystal. I just say the ratio. There's 1 sodium for every 1 chlorine, because it would be impossible for me to tell you how many sodiums or chlorines are in every single individual crystal, and that would be very confusing. So we don't do that. We just say the ratio. All of these compounds, ionic compounds, they form solid salts, crystals. They have these crystalline structures. And they are in these ratios. 2 Als, 3 Os. That's how they form their crystals. Okay? And so that's how we represent them in their empirical formulas. When it's covalent compounds, it's a very different story. Okay? Glucose. Glucose has a very distinct structure to it with an exact number of carbons, hydrogens, and oxygens. C6, H12, O6. Okay? That is the formula for glucose. I can't change the number because that would change the structure of this compound. If it only had 5 carbons, then it would change this. It wouldn't be in this same way. Okay? So this is a covalent compound. It is different than something that is ionic. If it's a covalent compound, I have to show how many I have of everything inside of that one compound. So sugar does form crystals, right? But they stack on each other. Those glucose molecules stack. They don't create crystal lattices with ratios. It's a glucose molecule on top of another one, and then they will pull apart once you dissolve them in water. But they are covalent. They are in this form. Okay? I cannot draw the structure of an ionic compound, not like I can for covalent compounds. Ionic compounds don't take on structures like this. They just have crystal lattices. That's all it is. Okay? So it's very different. Okay, so let's talk about molecular compounds. Molecular compounds are covalent compounds. Okay? So what distinguishes them? Well, you have a nonmetal and a nonmetal. So let's consider what's going on here. So metals, they lose electrons, right? Nonmetals do what? Gain electrons. Where do they get those electrons from? From a metal. So in the presence of a metal, the nonmetal has a stronger affinity for the electron, so it pulls the electron off of the metal. It just rips it off of it. That metal's fine with that. It doesn't want it anyways. So it goes to the nonmetal, and then they will come together. But what happens when I get 2 nonmetals together? Neither one of them wants to get rid of their electrons, right? They both have an affinity, a strong affinity for electrons. So they're both pulling for electrons. who's going to win? Well, if it's a covalent compound, a molecular compound, neither one of them wins. They share the electron. They share their electrons. They're unpaired electrons. They share them. And when they share unpaired electrons, it creates a pair for both of them. And now they're satisfied. They're happy with that. Okay? And they form covalent bonds. Covalent bonds are shared electron bonds. Yes?
Covalent bonds are like two nonmetals and nonmetals?
Yes. That's right. You have two nonmetals, and they will form covalent bonds because the nonmetals don't want to give away their electrons. They don't want to give them up. Okay? So, for example, you have an oxygen. Let's draw the valence shell of oxygen. How many valence electrons does oxygen have? 6. It has two S's that are paired, right? And then it has its p electrons, and it pairs one of them. It has two unpaired electrons. It doesn't like that. So it needs to find something that can fill those vacancies. It needs to find unpaired electrons from somewhere that can fill those vacancies. So in the presence of hydrogen, how many valence electrons does hydrogen have? Has one. It's unpaired, right? So hydrogen pairs its electron, its one valence electron, with oxygen. And then oxygen finds a second hydrogen and does the same thing. Now what have I formed? Water. Water is a pretty stable compound because we have filled all the vacancies. Okay? These electrons are orbiting hydrogen and they are orbiting oxygen. How many valence electrons does oxygen have there? 8. It now has 8, which is what it wants. How many valence electrons does each hydrogen have? 2, which is exactly what it wants. And so now they're very satisfied because they all have exactly what they want. Their valence shells are full of either 8 electrons for oxygen or 2 electrons for hydrogen. Okay? How about, so oxygen, let me draw it like this, I suppose. In the presence of another oxygen. Okay? They share those two empty spaces with each other. You form O2, which is the stuff we breathe. Oxygen doesn't exist all on its own. It doesn't go around with 2 unpaired electrons. It would be completely unstable, right? So it's not going to do that. It's not going to go around. It would just react with something if it was like that. So in that form, it becomes reactive. It would react. But oxygen in the air, it's very stable. Why? Because it's sharing electrons with itself. Okay? So it has satisfied its octet valence shell by bonding to itself. Oxygen does not exist as just a single oxygen. Fluorine does not exist as just a single fluorine. F2. Nitrogen does not exist as a single nitrogen. N2. They find each other, they bond to each other. That's how they exist. The nitrogen in the air that fills our atmosphere, it's N2. Okay? So they are satisfying their octets by bonding with one another and becoming stable in that way. Okay? These are molecular compounds. They're molecular compounds. They are sharing electrons. These electrons are shared there and they're shared there. Okay? I have formed a double bond here. One bond here, and they are sharing those electrons. Excuse me. Okay. So now we're going to start talking about how do we name these compounds. Okay? And this can be kind of tricky for people. Okay? But we'll try to work through it, and we'll do a little practice to make sure you guys are getting the idea here. Okay? So how do we name ionic compounds? When we name covalent ones, it's going to be so easy. You guys are going to be like, oh, this is amazing. I want to do it for everything. And that's where you get in trouble, because you start to try to name ionic compounds the same way you name covalent compounds, and you can't do that. Okay? When you name ionic compounds, you have to follow the ionic compound rules. When you name covalent compounds, you have to follow the covalent compound rules. Okay? So you cannot use one for the other. All right? All right, so how do we name ionic compounds? Step 1, determine the charge of determine the charge of the elements. If it is a metal from column 1 or 2, okay, we can easily predict the charges, right? The non-metal charge will be determined from its valence electrons as well. So we determine those charges. If it is a polyatomic ion, use the charge of the polyatomic ion. This is very important. No prefixes. No prefixes. You never, ever, ever, ever tell me how many things are in an ionic compound. You never do. You never tell me how many there are in an ionic compound. But that's exactly what you do with a covalent compound. You never tell me how many there are in an ionic compound. Okay? You only do it for covalent compounds. So the very first thing we do, using no prefixes, we name the metal. So whatever the metal is, we use its name. Calcium, so we'd use calcium in the name. Sodium, we would use sodium in the name. If it is a transition metal, if I had just said iron, it's a transition metal, I don't know which iron you're talking about. Is it iron plus 1, plus 2, or plus 3? Because I can't predict the charge here. So you have to tell me which iron you're using. Iron 1, iron 2, iron 3, to tell me the charge of the iron in the compound. Okay? So you use a Roman numeral to do that. The non-metal ending will be changed to "-ide". Okay? So, let's practice. The metal of the first one is called what? Sodium. The non-metal is what? It's chlorine, so I drop the ending and I end it with "-ide". Sodium chloride is this compound. How about the next one? K is potassium. Iodide. Potassium iodide. Okay? How about the next one? Sodium fluoride.
So if it's just the element, then you throw iodide in there?
Ide? Yeah. If it's the non-metal, the anion, so these are all cation ions, positively charged things are cation ions. The anion, negatively charged thing, always has the IDE ending if it's an element. Okay? How about the next one? This one's trickier. So this one, you would probably want to look up what HCO3 is, because that's the polyatomic ion there. Okay? So we could look that up, and it's bicarbonate. If it's the polyatomic ion, I simply use the name of the polyatomic ion. Sodium bicarbonate. That might sound familiar because that's baking soda. That's what you guys use in your cookies. Okay? Sodium bicarbonate. Okay, Does anybody know what this one is? CO3? It's a polyatomic ion.
Carbon dioxide.
No, it's not. It's an ion. It's a polyatomic ion. What's the name?
Carbonate.
Carbonate. CO3, 2 minus. Carbonate bonds with 2 sodiums because each sodium has a +1 charge. So this is sodium. Okay. The only difference between carbonate here and carbonate here is that you added a hydrogen to this carbonate, which made it bicarbonate. Okay? You don't have to remember that one. But the carbonate, I do expect you to know. Oh. I think that got written incorrectly. ClO. Okay? Sodium, what is the polyatomic ion ClO? Do you remember what chlorate is? Okay, this is hypochlorite. Okay? ClO is hypochlorite. Chlorate is ClO3. ClO2 is chlorite. Hypochlorite would be ClO. Sodium, it's another pretty common one. Bleach. Okay? Calcium carbonate. OH, that's hydroxide. That's another one we'll learn. Hydroxide, OH. Okay? OH is hydroxide. That's going to be a very common one you're going to have to know, especially when we get into acids and bases. Actually, do we get that? Maybe you don't get into that till next semester. But hydroxide, very common. Okay? So magnesium hydroxide. That's fun stuff. Anybody ever had any milk of magnesia? Yeah? Okay. Won't talk about what it does to you, but what's this one then? Yes. Okay. Aluminum hydroxide. Sodium hydroxide. Okay? So that's how I'm going to name these compounds. I never say how many I have. Okay? I don't say disodium carbonate. Yet, why? Why didn't I have to say disodium carbonate? Yes, because it's ionic, and this is what I know. I know the charges. If I know what there is, if I'm given just the name sodium carbonate, I know sodium has a +1 charge. I know carbonate has a 2- charge. So the formula is Na2CO3. Did you have to tell me there was 2 sodiums for me to come up with that? No. That's why you never tell me how many you have. You don't say it. If you do, it'll be wrong. Do you think disodium carbonate might be an answer choice? Yeah. Do you choose that one? No. You choose sodium carbonate. You're going to be so tempted to choose disodium carbonate because it looks so right to you. Oh, that makes so much sense. Don't do it. Resist the temptation. Okay? It's not disodium carbonate. It is just sodium carbonate. All right, we'll see you guys next time.